Hey everybody, Lesson 7, we're looking at analyzing rational functions today. We're going to explore and refine our techniques for graphing rational functions a little more in detail today. Last time we had developed a procedure that was 4 or 5 steps long, and today we want to add into those steps, maybe thinking about symmetry, and talking about whether the graph lies above or below the x-axis and how to put all of that together to draw a rational function when you don't have access to a calculator. So first of all, we can look at the numerator and notice that -1 is a 0 of the function. So I'm going to put -1 on my number chart. I know it's a 0 of the function, and I can put a little point right there at that location. That came from our numerator, the 0 of the numerator. In the denominator, we could factor or use the square root technique, and we know that -3 and +3 would be vertical asymptotes on our graph. So the domain's going to be restricted at -3 and +3. Now, notice how this kind of creates little segments or intervals on the number line where we can consider the behavior. So I want to pick a point. If I pick a value, let's say we pick -4 over here, and we could pick in this interval -2, and in between -1 and 3, we could pick 1. And after 3, we could try 4. So when you think about the behavior and you're testing -4, if we plug in -4 into our function, we're going to end up with a -3/7. And the sign is negative, which means the graph is going to be below the x-axis. You really don't have to determine the specific value, but in this case I'm doing that just for the effect, so I know I have a dot right here somewhere, -3/7. And then doing the same thing at -2, if we substitute -2 into the function, we end up with +1/5. So when the sign of the y value is positive, the graph would be above the x-axis. When x is -2, we're hovering really close here. Continuing on, if you substitute 1 in there, we're going to end up with a -1/4, which is a negative y value. So the graph would have to be below the x-axis on the other side of the y-axis. And substituting 4, we're going to end up with a +5/7. It's positive, so the function graph would be above the x-axis. Now, the other thing we didn't check on in this particular case is you notice that the horizontal asymptote, the power in the numerator is 1 and the power in the denominator is 2. So we know that we have a horizontal asymptote at 0. So we could sketch that in. And we know at 4 we had a positive number. So in this case, if I started over here on the left, we don't have any symmetry. Is there anything we've left out? Yes, we have left out what's the y-intercept value. So substituting there, if these numbers are 0, we end up with -1/9. So you also know that when x is 0, y is -1/9. And we said we had a y = 0 was our horizontal asymptote. So putting all that stuff together, we can see the behavior here, and we can see that the graph is negative over here, positive over here, and with the asymptotes drawn in, starting below the x-axis, you have to stay very close to the asymptote, go through that point at -4, and you have to turn and go down because we can't cross the vertical asymptote at -3. Likewise here on the other side of the asymptote, we have to be upward bounded to follow that pathway, but when you cross the x-axis and through the y-intercept, you cannot pass x equals 3 on the other vertical asymptote. So it has to stay between those asymptotes. And then in the last segment on our interval, my y value is positive, which means, again, I'm going to hover close to the vertical asymptote, pass through that point, and stay again close to the horizontal asymptote. So that's the kind of procedure we're trying to develop and just sharpen our skills in this lesson. Here's another one that we want to try. So in this case, I'm going to factor the numerator. No, the numerator won't factor. So let's grab a piece of paper. We need to figure out what the intercepts are. And if it's x squared plus 3x minus 2, and that won't factor, I can use the quadratic formula and do opposite b plus or minus the square root of b squared minus 4ac, 4a times negative 2, that would be 8, all divided by 2a. So my x and y intercepts are going to happen at square root of 17 over 2. So jump into a calculator. One of them is going to be negative 3.56, and the other 0 is going to be positive 0.56. So we need these two, which is a little more complicated. Negative 3.56 was one of our zeros, and positive 1/2 was the other 0. And you see here from the denominator, we have a vertical asymptote at negative 2. So let's go sketch that in. Vertical asymptote at negative 2. We know one of the solutions is negative 3.5 roughly. We know the other one is about roughly 1/2. And we want to test some points. We can also substitute 0 for all the x values and figure out that the f of 0 is, what is that? Negative 1/4. Negative 2 divided by 4 is negative 1/2. So when x is 0, y is negative 1/2. Now another thing I notice is we have the power in the numerator is 1 degree larger than the power in the denominator. That tells me we want to use synthetic division. It'll have a slant asymptote. So the vertical break was at negative 2, and it was x squared plus 3x minus 2 using synthetic division. There we have our slant asymptote. The depressed polynomial is x plus 1. So we know y equals x plus 1 is a slant asymptote. And we can sketch that in. Y equals x plus 1 is going to be on the diagonal like such. Okay. Am I following that line? Pretty closely. And already we know pretty much how the graph's going to go, since we have a point here and it's going to cross the axis. It's got to go that way, and it's got to go down here, stay close to the slant asymptote. This one's going to do the same thing, and it's got to pass through 1/2 and then go up that way. So nothing is in this section and nothing is in that section. But just to verify that for you, let me show you what I'm thinking of. If you substitute negative 6 into this function, your y value is -2, with that negative sign, you're below the axis. In this interval, if we tried -3 and substituted -3 into the function, you end up with 1, which is positive, so your graph is above the x-axis. In between -2 and our 0, if we tried -1, our y value is again -2, so a negative sign means the branch is going to go below the axis. And then finally I picked 2 because that was an easy one, and I ended up with 1, which was positive, so your graph lies above the x-axis. So in between here, your test point and your value, you have the ordered pairs. -6, -2, -3, +1, -1, -2, and +2, +1. So you can see that we did stay on that curve, and once you know the behavior in a region, once you know a few of those points, you can just follow close by the asymptotes and sketch that graph in there. Okay, here's another one, example 3. We've got x to the 4th over x squared. So you know x can't be 0 because that becomes a vertical asymptote. And this one we're actually finding an end behavior model. So by that I mean I want to divide x squared by x to the 4th. So if you divided x squared by x to the 4th plus 1, you don't have any values for the cubed term or the squared term or the linear term. But you know x squared will go into x to the 4th, x squared times, to give us that. And when you subtract, you need to bring down this 1, and you need to bring down, that's it, right? You need to bring down the 1, so we have our +1 for the end behavior model. So since x squared was our end behavior polynomial, I can't really call it a slant asymptote. It's not a slant asymptote, but this is our end behavior model. I'll show you how that goes here with our function. We know we can't have x being 0. We don't have any, the numerator can't be 0, so there's no zeros of the function. And it is going to be an even function, so it's going to have y-axis symmetry. So we know a few things about the behavior of the graph. And if I tested a point on either side, I could test -1 or +1 into the function. And by doing so, when you square a negative number and raise a negative to a 4th power, you're going to get 2 on both sides. They're both positive, which means our graph is going to be above the axis in both cases. And we have 2 points, -1, 2, and +1, 2. We also know that there's a vertical asymptote on the y-axis at x equals 0. So here's what I mean by this end behavior model here. You know, the parabola x squared looks something like this. So we're off the graph. Sketch that in there. And here's what's going to happen. This graph is going to come from positive infinity. It's going to touch the point 1, 2, and then not cross over the vertical asymptote at 0. Like such. So it's got two funny little shapes in there that are sideways slanting parabolas of some sort, parabolic shape, and they hover next to this end behavior model of a parabola. So the parabola is behaving like asymptotic behavior for the blue graph. The blue pieces are the graph of our rational function. And you could check that on a calculator. My picture's not that great with my stylus here. Okay. Then in example 4, we can actually factor the top and bottom here. So let's see, what do we got? 2x times x and factors of 2. If we had a negative 4 there and a negative 1 here, we could get that negative 5 in the middle. And then the denominator is going to be x minus 2 times x plus 1. So here we have a point discontinuity at 2. So we could take 2 out of there. And if you substituted 2, we're going to get 4 minus 1 over 2 times 2 is 4 minus 1, that's 3, and 2 plus 1, so we're going to get 1 for the location of the hole. So that was pretty easy. The ratio gives me y equals 2 is my horizontal asymptote. So we can go sketch that in. We have a vertical asymptote at negative 1. And what happens if you substitute 0 into the function? If we put a 0 in here, we're going to end up with 0, negative 1. And if you solve 2x minus 1, we're also going to get a, let's see, we're also going to get a half is going to be our 0. So we've got a 0 there, a vertical asymptote here, a horizontal asymptote at 2, and we need to pick some values. So we can't have, let's see, we could have negative 2, we could have positive 2 over here. I guess if we picked a number in between, what did we have if we picked 0? Did I write that down? We had, if we picked 0, we had negative 1, so that would be below. And we had the h of 2 was 1, that was a hole there, so we got to draw that in. So let's go here. We got a hole at 2, 1. We have 0, negative 1. So we know the behavior over here is a branch that's going to cross like that. And what did we know about? Oh, we also knew 1/2, 0. This was a 0. Okay, so we got a hole, we got a 0 at a half, and we have a y-intercept at negative 1. On this side, we need to substitute negative 2. So substituting negative 2 here and here, you end up with a positive 5. So the graph has to be above the axis. Negative 2, positive 5. So it's going to stay close to the vertical asymptote and go through negative 2, 5, and then turn and go that way. All right, so you see how I'm using the number line and picking a test point in each section. We knew this was a hole, drew the hole on the graph, and then factored, substituted, followed all 8 steps of that procedure to end up with that graph. So in this next example, before we get into the word problems, we have 2 word problems. This one, we're given a graph and we have to come up with some type of an equation that would represent this graph. So let's say if x is 0, you see right there, you have a numerator factor has to be x because we have the ordered pair 0, 0. So that's got to be in the numerator as a factor. The factor is going to be x. We also have a vertical asymptote at +2 and -2. So these have to be factors in the denominator in order to make an infinite discontinuity, which is going to make +2 and -2. So our factors are going to be x +2 and x -2. That's how we get those vertical asymptotes. Now, we also have a horizontal asymptote at 0, right? So if we have x squared -4 and we have x in the top, let's check this out. So could we get, because here's what we've got to think about, could we substitute 1 into here and end up with a positive number? So if I substitute 1, I do not get a positive value, which tells me that we need to put a negative in our numerator. And I also noticed this. Let's try this. When you get -3, it looks like you have a number a little bit bigger than 1. So let's think about that. If you put -3 in the numerator and -3 in the denominator, we're going to get 3/5. So that's not bigger than 1. So I'm thinking, how about if I have a factor of 2 there? And if I had a factor of 2 there, then I would have a number that's a little bit bigger than 1. And will the same thing work over here at +3? Because I want the same thing, only just a +3 and a +3 would give us a -6/5. So I have some form of a rational function that could describe the graph that's shown in that picture below, using that kind of logic and that kind of reasoning. I used origin symmetry, I used where the 0 was, I tested some points, and let's see, do we have y = 0 for a horizontal asymptote when the power in the top is smaller than the power in the bottom? I think we're good to go there. Okay, 2 more examples and then we're done. We want to find the dimensions of a rectangle with a minimum perimeter if the area is 300 square feet. So if area of a rectangle is length times width and the area is 300 feet, and we've got perimeter that we're looking to find a minimum for, perimeter is 2 times the sides and 2 times the width. And we could take the length and get a name for the width, get a name for the length in terms of the width. And if I substitute 2 times 300 divided by the width plus 2 widths, we have a perimeter formula in terms of width is 600 divided by W plus 2W. So I'm going to take that function, go to my calculator, graph that 600 divided by x plus 2 times x, and then we're going to use the feature on the calculator to find the minimum value. And our minimum is 17.32 and 69.28. So what does that tell us? You could draw a little sketch of that here if you wanted. 17.32 and 69.28 was the minimum. And here's what we know. We know that the width of the rectangle that has a minimum perimeter and an area of 300, the width is about 17.32 feet, because our dimensions are in feet. And we also know that the minimum perimeter would be about 69.28 feet. And if you multiplied these two together, we should get that area, the length. We'd have to figure out that width is 17.32. So what's the length? We have to go figure that. So 300 divided by 17.32 would be the length. And the length is also 17.32. So it would be a square. And then we could check that out. Is 17.32 squared close to 300? And looks like it is 299.98. Okay, so the length and the width would both be 17.32 to have a minimum perimeter. So we found the dimensions of the rectangle. And then here's our last one. Acme Can Company is marketing a new 1-liter cylindrical can for an orange juice concentrate. That looks something like this. And we want to find the radius and the height of the can if the container is going to have a surface area of 1,000 centimeters squared. So we've got the height and circumference or the dimensions across here. There's a radius here, so the distance across would be 2 times the radius. And we know 2 different equations. We know an equation for the volume is pi r squared h, and they told us the volume is going to be a liter, which is 1,000 cubic centimeters. So pi r squared h. And I'm going to solve for h in this case. So we have 1,000 divided by pi r squared. Now surface area is this formula. So the surface area is 2 pi r squared. I have to erase my fancy orange juice can. Okay, so the surface area is going to be 1,000 centimeters. So surface is 1,000, 2 pi r squared plus 2 pi r h. And we're putting this in place of the h. So 1,000 is 2 pi r squared plus 2 pi r h, substituting our name for h into this equation. So we can get rid of the pi and one of the r's and have 1,000 is 2 pi r squared plus 2,000 divided by R. So here's what we're going to do. We're going to go to our calculator. We're going to graph one equation as 1,000 and another equation, we'll call that one Y1 and this one Y2. And we're going to look at the intersection of those two graphs. So we're using solving with the calculator. Okay, so getting rid of those two equations, we're putting in 2 pi where did it go? I lost it. R squared, so I'm using x in place of the variable r, and 2,000 divided by x. So there's one equation. And then the second equation is 1,000. Whoop, need to be in the equation part. 1,000. And we have to set our window right. So my window, I think I'm going to go up to 50, 0 by 50 ought to work. Whoop, not 1,050, 50. And then on my Y, I'm going to go up to about 1,200. Whoa, that's a mess there. 1,200. There, so I want the intersection right there. So menu, analyze, we want an intersection. So from there to there, one intersection is at 2.05. And menu, analyze, intersection. And the other intersection is at 11.462. So I'm going to get back to my screen here. And this is what we know. So there's two possible sizes, two possible cans. One can be tall and skinny, and the other one can be short and fat. So two different sizes. The first one, radius, had a size of 2.054. And you know my height formula is 1,000 divided by pi r squared. So if we substitute 2.054 into this height, our height on the first can is about 75.44 centimeters. And then the second can had a radius of 11.462 centimeters. And again, if I put this number into height, the height of the second can is about 2.42 centimeters. So this one would be a tall, skinny can, which is probably the size that the company would use, where this one would look like a tuna fish can, you know, or a cat food can. It would be long this way and very short, where this one would be tall and thin. And if you've ever bought frozen orange juice, you know, it would look something like that, most likely. All right. See you next time. One more lesson to go in this unit, and we're done. Bye.